Okay, so this is the next question we need to solve. So firstly, we can just go and assume let f of x1, x2, x3 equal to this. We need to write the actual statement, okay, but I just wrote it in short because I got bored or something. Yeah, and then for the constraints, we take let h1 is we have two constraints, no? So we'll need two of them. First is h1, that is this rule, and we shift the 13 to the other side, so we get minus 13. This is h1, and let h2 equal to this. This is our h2. Okay, so now we need to first define a Lagrangian function. So a Lagrangian function looks something like this, I guess. x1, x2, x3, and we'll also have lambda 1, lambda 2. So we get f of x1, x2, x3 minus lambda 1 h1 minus lambda 2 h2. This is a slightly lengthy sum, but fine only. So our function is x1 square plus x2 square plus x3 square minus lambda 1 times our first constraint, which is x1 plus x2 plus x3 minus 13, and a second constraint, which is lambda 2 times 3x1 plus x2 plus x3 minus 27. Nicer. Now, since we have 1, 2, 3, 4, 5 variables, we need to differentiate our Lagrangian function with respect to each one of them, one at a time. First, we differentiate it with respect to x1, then we differentiate it with respect to x2, then we differentiate it with respect to x3, then once with our lambda 1, and once with lambda 2. And each time after differentiating, we put it equal to 0. So for the first one, let's see, our first differentiation is basically 2x1 minus lambda 1 minus 3 lambda 2 equal to 0. Now for the second one, we get with respect to x2, no? So for the second differentiation, we get del by del x2, so 2x2 minus lambda 1 minus lambda 2 equal to 0. Our third differentiation means with respect differentiation with respect to the third variable gives us 2x3 minus lambda 1 minus lambda 2. And then we can also differentiate with respect to not the fourth, means it's the fourth variable, but not this one, which is lambda 1. So we basically get our constraints back now, x1 plus x2 plus x3 minus 13 equal to 0. And in the other one, we get x1 plus x2 plus x3 minus 27 equal to 0. Now over here, firstly, we label our equations. I cannot use my calculator because I can solve only 4 equations simultaneously. And over here we have 5. So first we need to reduce our equations. So the most easiest way is by equating equations 2 and 3. As you can see, by doing so, we'll get some value. By equating 2 and 3, 2, we would get 2x2 minus lambda 1 minus lambda 2 is equal to 2x3 minus lambda 1 minus lambda 2. So this gets cancelled, this gets cancelled, this gets cancelled, this gets cancelled. So we get x2 equal to x3, correct? Now using this one condition, okay, we got it from these two now. So these two ka work is done now, okay. So now we got x2 equal to x3. Now we can substitute that right over here. If you put x2 equal to x3 in this equation, okay, we would get in equation 4, that is. Let's move on to the next page for it. put x2 equal to x3 or x3 equal to x2, both mean the same thing. So I'll put x3 equal to x2. Okay. If you put it in this one, we'll get we'll get x1 plus 2x2, x1 plus 2x2 minus 13 equal to 0. So we'll get x1 plus 2x2 minus 13, I'm shifting it to the other side, is equal to plus 13. And this is a new equation, take it as a. And if you substitute x2 is equal to x3 in equation 5 as well, we'll get x1 plus 2x2 minus 27 equal to 0. And on shifting it to the other side, it becomes plus 27. Yeah, I think I messed up a little. Okay, this is supposed to be 3x1. Yeah, that's all I messed up. This is 3 over here. So even over here, we'll get 3x1. That's all. So put this in equation 4 and 5. Now, we are only concerned with values for x1, x2, x3. No, we are not concerned with lambda 1, lambda 2. They are not going to be of any use to us whatsoever, in this case at least. So we can just proceed by solving for these two equations. Now, these two equations are simple enough to solve, but I shall solve it with a calculator. So, two variables and two equations. We get x ka value as x1 as 7 and x2 as 3. x1 is 7, x2 as 3. Now you may ask, how do we find x3? We already found out by equating our equations 2 and 3 that x2 is equal to x3. No? So whatever value we get for x2, x3 should be the same as it is. So therefore x3 is also equal to 3. So we get 7, 3, 3. Therefore our stationary point x0 is 7, 3, 3. Nice. So now we need to check whether this point is a point of minima or maxima. For that, since we have 3 variables and 2 constraints, which is very, very sad, we need to calculate the phi. Me, ha ha ha. Pretty huge it is. So we'll get 4 zeros here. Then differentiation with respect to the constraint 1, x1, x2, x3, and same thing will be repeated vertically here. We also have a second one, second constraint, that is and that will also be repeated vertically just as it is there. Then we'll be differentiating our Lagrangian function with respect to x1. These are the diagonal elements, okay, with respect to x2, with respect to x3. Then we'll have x2, x1 and x3, x1, and these ones will be just those reversed. Del square L by, this is x1, x2, no? So this will be del x2, x1. This is del x1, x3, no? So this will be del x3, del x1. Over here we'll get del square L by del x2, del x3, and here we'll get the reverse of it, del x3, del x2. Nice, sir. Now we need to calculate this. And over here, if we have this thing, what do you say? If del phi ka sign comes as positive, no? if we get positive, then we'll have a minima at our point. However, if del phi comes as negative, then we'll have a maxima at our point, the stationary point, that is. Let's see what it comes as. This is the only thing we need to calculate though. Those remain the same. I'm going to calculate the constraints ka thing first, because those are the easier. Okay. You just need to look at the coefficients in general. So we get 1, 1, 1 and 3, 1, 1. Like basically if we calculate the derivatives also, you'll get the same thing. Like this one. Del h1 by del x1 is 1. Del h1 by del x2 is also 1. Del h1 by del x3 is also 1. And same for this thing also. Del h2 by del x1, only x1 ka thing will remain, no? All others will go. So 3. Then del h2 by del x2, only x2 coefficient remains. And last one, del h3 by del x3, only x3 ka coefficient remains. So we get 1, 1, 1 and 3, 1, 1. So 1, 1, 1, 1, 1, 1, 3, 1, 1, 3, 1, 1. I don't think we need this extra part over here. Right here. Now we need to calculate the Lagrangian function derivatives. For that, we can just directly look at them. As you can see, each Lagrangian function, let's say if we differentiated this with respect to x2, okay, like del x1, and then we differentiated with respect to x2, this is x1 and then x2, we would get a 0, no? Same thing, if we differentiated this with respect to x3, then also we'll get 0. And if you look at this also, this one, if we differentiate this with respect to x3 first, del x3, and then x1, or we differentiate this with respect to del x3 first and then del x2, we would get a 0, no? If you see, the only place where we are getting non-zero values is when we differentiate it with respect to themselves only. That is, when we calculate this over here, we'll get 2. Similarly, when we calculate del square L by del x2 square, we'll get 2. And lastly, when we calculate, these all are 0, 0, 0, 0, 0. And lastly, when we calculate the derivative with respect to x3 twice, we also get 2 again. So basically, these diagonal elements come as 2. In general, this is the case, okay? But sometimes, like in trick question, these do not become 0. But most of the time, these do reduce down to 0. Now, we just need to simplify this using a few column transformations. So we could use this column. Let's say I want to use this column, okay, the second one here. So I'm going to do, this is column C4. So I'm going to do C3 is equal to C3 minus C4, and C5 is equal to C5 minus C3. C3 is equal to C3 minus C4. C5 is equal to C5 minus C3. So that will give us, the first two columns will remain unchanged. This column, if we subtract, we get 0, 2, 2, minus 2, 0. This column remains as it is because there was no modifications made. And this one over here almost becomes 0. Now, since this one, basically the signs, okay, for the sign, this is positive, negative, positive, negative. Since there's a negative sign for this one, this is just like a trick to remember, okay? So since there's a negative sign for this one, now when we reduce it to a 4 cross 4, it's del phi only, but when we reduce it to a 4 cross 4 one, the one that is present here, or basically the element that is present here, will come with a minus sign, and then since we took this element, no, so we eliminate this row and eliminate this column, okay? So now our matrix will be 0, 0, 2, 0, 1, 3, 2, 0. We ignore this one, this row, and this column, and write the matrix as it is. So we get 0, 0, 2, 0. Then we have 1, 3, 2, 0, 1, 3, 2, 0, 1, 1, minus 2, minus 2, 1, 1, minus 2, minus 2, then 1102. 1102. Sounds good? Okay. Now since I can solve 4 cross 4 matrices with my calci directly, that is what I'm going to do. I do not want to reduce it any further. 0 0 2 0 1 3 2 0 1 1 minus 2 minus 2 1 1 0 and 2. Yeah, I entered the matrix. Now going to matrix calculations, determinant of matrix, you get minus 16. However, remember there's a minus 1 here, so minus 1 into minus 16 gives us positive 16. Therefore this is positive. As this is positive, as I said before, in this case if we get del phi as positive, we will have a minima at our point, and if we have del phi as negative, then maximum. Since del phi is positive at a stationary point that we calculated before, that is 733, we have a minima. This rule can be used for this thing, 3 variables and 2 constraints, basically. Yeah, so now in order to find the minimum value, we just need to substitute 733 in a function. So basically, if you see, a function is basically just 7 square plus 3 square plus 3 square, which gives us a total of 67. So the minimum value of a function at 7 comma 3 comma 3 is 67, and you can write it like this also, 67. Nice.